Looking at our grade book to see what was due, we should be finished with Module 1 now. The test was due this weekend, so you should have had the practice test completed and parts 1 and 2 of the Module 1 test. So if you're not finished with Module 1, you are behind. So you need to get caught up as soon as you can. Make sure you look at those lessons, get those assignments done before you do the test, because I want you to do well in the test. It's worth a lot more points than those lessons are. So you need to make sure you do well in those by reviewing the lessons and doing well in the other assignments first. If you didn't do well in one of these assignments, go back and take it again. Look, see what you missed. Go back and study that. Take it again. I want you to do well. So this week, we are starting Module 2. As you can see on our due dates over here in the grade screen, the first 2 lessons are due this week, 2.01, 2.02, functions and their properties and graphs of functions. So that's what we're looking at today, is functions of their properties and graphs of functions. So let's go ahead and look at the lessons. The lessons are going to look a little bit different than this unit. Algebra 3. Look a little bit different. This time they're Google Docs for the lessons. Let me go to the first lesson. All of the lessons on one page. This is all on one page here. It's 7 pages, but I mean, you don't have to go to page 2, page 3 by clicking to other pages. It's all right here. So let me make this a little bigger for your screen. All right, so this has the scenic overlook. Like I said, Algebra 3 is, we pull lessons from pre-calculus. We pull lessons from Algebra 2. Algebra 3 is an Arkansas-only course. And so we cover all of the materials we need by stealing from other classes. So this has a scenic overlook. It'll tell you basically for this lesson, most situations we encounter in lives follow a cause and effect relationship. If we do something, there'll be a result. In mathematics, that rule corresponds to known as a function. So when you put something into a function, the function changes and it comes out different. Functions in our lives. If we drive on the interstate at 70 miles an hour while traveling to Yosemite National Park, how far would we travel in a given number of hours? That would be a function. For 3 hours, you would drive 210 miles. That's what the function would give you. You put a 3 in, you get 210 out. If I were to purchase a certificate deposit, paying 4.5% interest per year, how much would it be worth after a given number of years? How much money did you earn on your certificate of deposit? If I were hiking on the John Muir Trail and could hike 12.5 miles a day, how far could I hike at a given number of days? Those are all functions. And we can make a table. Like here's the driving to Yosemite. 1 hour, 70 miles, 2 hours, 140, 3 hours, 210. See, we can make a table to represent the function. Or we could use these ordered pairs. 170, that's an ordered pair. 2, 140, 3, 210. Those are ordered pairs, the X and the Y, the X and the Y, the X and the Y, the X and the Y. So the definition of a function. Now, this is a very college type definition of a function. A function f from a set A to a set B is a rule of correspondence that assigns to each element x in the set A exactly one element in set B. The set A is the domain, or the set of inputs, of the function f, and the set B contains the range, or set of outputs. Very college-y, wordy sounding, doesn't it? Very mathematician sounding. What does that mean? Well, we've always talked about a function in high school, but for every x, there's only one y. That's what it is. For every x, there's only one y. For 4 hours, there's only one value that goes with 4, 280. That's the only value. So this is a function. For 6, there's only one value. For 7, there's only one value. For 2, there's only one value. There's only one y for any given x. That's what that means. And the x's are the domain and the y's are the range. That's what this whole definition of function breaks down to in more layman terms rather than mathematician terms. So let's look at the characteristics of functions. For each value in the domain, there's only one corresponding value in the range. For each x, there's only one y. Right? X is our domain, y is a range. All elements in the domain must be used, and more than one value in the domain can be matched with the same value in the range. Up here, if we're looking at hours since we left, if we stop for lunch and we spend an hour, maybe hour 3 would be 210, and now hour 4 would be 210 because we didn't travel anywhere. We stayed there, had lunch. That's still a function because there's still only one y for each x. Now, there's two different x's that have the same y. They both be 210, but each x only has one y attached to it, even if it's the same y as someone else has. So test your skills. Now, here's a place in these programs, even though this is just like a Google Doc, it still has places where you can practice, because that's important that you be able to practice as you go through the lesson. So this says use the values of 1, 2, and 3, 4 as the domain. And here's the range, -2, -1, 0, 1, 2. Which of the following ordered pairs represents valid functions? So you look through each of these and figure out which of these is a valid function. And then we can click here and check our answers. So let's see, A, 4, 2, 3, 1, 2, -1, 1, -2. Each x, the 4, the 3, the 2, the 1, each x only has one y. So this is a function. Let's look at B. 2, 1, 4, 1, 1, 0, 3, 0. Each x, 2 only has 1, 4 only has 1, 1 only has 0, 3 only has 0. Each x only has one y, so that is a function. Now, 1 and 3 both have the same y, but they only have 1, so that's okay. Look at this one. C, 4, -2, 4, -1. Oh, right away, we see it's not a function because the value 4 as an x has more than one y. It has -2, it has -1. It also has 0, it has 1, it has 2. There's 5 y's attached to the exact same x. C is not a function. 1, -2, 2, -1, 3, 0, 4, 1, 5, 2. 5 is not part of our domain. So this does not fit because it's using a value outside of our domain. Without this last one, that certainly is a function. Let's see. 1, -2, 2, -1, 3, 0, 3, 1, 4, 2. 3 has two different y's attached to it, a 0 and a 1. So that's not a function. 1, 1, 2, 2, 3, 1, 4, 2. Okay. 1, 2, 3, 4 is our x's, so that doesn't repeat. 2 of them have the value 1, but still there's only 1 for each x. So if we click check your answers, it'll pop up another window for us where we can check our answers. All right. Before our assessment here. Let's see if I can make this page a little bigger to see. There you go. A is valid since the value in the domain matches one element in the range. Each x only has one y. B is valid. C is not valid because 4 has more than one y. It has 5 different y's. This is not valid because it includes numbers not in the domain. Like we said, that 5 is not part of the domain. This is not valid because 3 has 2 different y's. And this is valid because each one only has 1. 1, 2, 3, 4 different x's. So that all works nicely. So you can check your answers on these practice problems in here. So functions in algebra. In algebra, we're familiar with expressions that we represent with an equation, right? Often the set of ordered pairs can be shown as an equation with two variables, like 2x minus 1, y equals 2x plus 1, creates the ordered pairs for values of x. So for every x you put in that equation, you come up with a y. So the x is called the independent variable because we can assign whatever values we want. We can't assign the y. The y is dependent on what the x is. Whatever the x is will determine what the y is. So what would be the range for the equation y equals 7 minus 3x if the domain is between -4 and 3, but does not include -4 and 3? So what we would do is we would substitute -4 in and get a value, and substitute 3 in and get a value, and know that the range would be the numbers in between there, but not including those. So here, the answer would be -3, -2, -1, 0, 1, and 2. And the domain would be these. Oh, I'm sorry. The domain would be those numbers because it's everything between -4 and 3, right? It's all those values in between there. And there's the range because when we substitute those numbers in, that's the y's that we would get. So that is the range for that domain. So determine the range for the following with x. So here's another one for you to practice. Check your answers. All right, let's talk about function notation. I'm not going to do all these example problems because you can read this on your own. This is your responsibility to go through the lesson. But I'm going to pull key points out of here to make sure you don't miss it. Function notation, right? We always say y equals But we can also say f of x equals, because they're the same thing. If we write it f of x equals, that's function notation, right? Function notation. So y equals 7 minus 3x is the same as f of x equals 7 minus 3x. Okay. The domain is all the valid numbers for x. All right. So if we have f of x equals 1 minus x, it's all real numbers. If it's 1 over 1 minus x, well, let's look at that one. I'll put that on my paper. Let me get, no, it's a graph paper. It's a regular paper for this. Here we go. So if we have f of x equals 1 over 1 minus x, what is all the valid domain for that? Well, this is a fraction. We know a fraction cannot have a 0 on the bottom. No, we cannot, because we cannot divide by 0. A fraction says take the number on top divided by the number on the bottom. We cannot divide by 0. So anytime that this is a 0, that is not valid. So when is that 0? 1 minus x equals 0. Subtract 1 from both sides. Negative x equals negative 1. Divide by negative 1. When x equals 1, this is 0. 1 minus 1 equals 0. So the domain is all real numbers except x equals 1. The domain is everything except for when x equals 1. For that equation right there. The domain be all real numbers except 1. Because you can't divide by 0. All right. So here, determine the domains of these. See this one, x minus 2. So x cannot be 2. Because 2 minus 2 would be 0, and that would be on the bottom of the fraction. What about this one? Now, let's look at this one. Let's put that on our paper. F of x equals the square root of 20 minus 2x. Okay, 20 minus 2x. What's the valid domain for that? Well, what are we restricted to? If we have a square root, and let's say that's y, is there any number that y cannot be? Put that in the chat. What can y not be? What's not a valid number for y? Can y be 0? Could you take the square root of 0? Sure, 0 times 0. So the square root of 0 is 0. 0 is a valid number. What's not valid? Waiting. What is not a valid number for y? If we have the square root of y, we're restricted. Y cannot be just any number. What can y not be? No, the video is not frozen here. We're waiting for an answer from you guys. What number can y not be? Well, you guys are in Algebra 3. You know this. Y cannot be certain numbers. Can it be 4? Can I take the square root of 4? Absolutely, it can be 4. Square root of 4 is 2. Square root of 0 is 0. Square root of negative 9, what's the square root of negative 9? Square root is a number you multiply by itself, right? To get back to the original number. Because square root of 4 is 2, so 2 times 2 is 4. The square root of 4 is also negative 2, because negative 2 times negative 2 is 4. So there's 2 square roots for square root of 4. Square root of 0 is 0, because 0 times 0 is 0. Oh, you guys are going to struggle in this assignment. Okay, embarrassingly so. I'm going to have to tell you the answer because nobody knows it. Y cannot be a negative number. Negative 9. What's the square root of negative 9? Well, it's not negative 3 because negative 3 times negative 3 is a positive 9. It doesn't get you back to negative 9. It's not 3 times 3 because that's positive 9. There's no way you can get a negative number when you multiply the same number by itself twice. Y cannot be negative. Y has to be greater than or equal to 0. So anytime this is negative, it's invalid. It's invalid. So this has to be at least 0. So 20 minus 2x has to be at least 0. So subtract 20. Negative 2x equals negative 20. Divided by negative 2. So x equals 10. So if x equals 10, this is 0. That's okay. That's okay because we can be 0. But which way do we need to go? Can x be larger than 10 or can x be smaller than 10? One of those does not work. Let's say if x is smaller than 10. Let's say if x is 5. 20 minus 2 times 5. 2 times 5 is 10. So that'd be the square root of 10. That's a valid number. If x is larger, let's say x is 20. Let's pick one. Just pick. So 20 minus 2 times 20 is 20 minus 40. That's negative 20. We cannot take the square root of negative 20. So that means if it's bigger than 10, it's not going to work. So x has to be less than or equal to 10. That's our domain. Any x that is 10 or smaller will work in here. And you say, well, if smaller, that means it could be negative 10. Sure. 20 minus 2 times negative 10. Negative 2 times negative 10 is plus 20. So it'd be 20 plus 20. That'd be the square root of 40. That's okay. So x could be a negative number because it's subtracting it. So you just have to calculate what valid numbers you can put for x for the domain. And then the range is going to be, well, when x equals 10, that's the largest it could be. And that'll be 0. So the y's could be greater than or equal to 0, right? Because we can take the square root of any number and it'll be at least 0 or bigger, but it will never be a negative number. Square roots will never be negative. All right. And you can do that here. When we click check your answers, it'll give you the answer here. There it pulls up. There you go. X less than or equal to 10. Because we just calculated x equals less than or equal to 10 as our domain. That was for that one. All right, let's move down. Okay, this up here, this was the summary, the scenic overlook, the summary. When you get down to this part, this starts the actual lesson in more detail. So the top part is the summary. So this talks about it again in more detail. The domain, the range of a function. Every element has a unique element in the range. All right. Function notation. Y equals f of x. You can read this, a function, not a function, bit of history. You can read this information. I'm not going to read everything to you. Okay, defining the function. Does y equals x squared define y as a function of f? Yes, because for every x, there is only one y. Substitute any x you want in there, you'll only get one y. You won't get more than one y for any x in there. Let's see. Oh, graphs of functions. If we have a graph and we want to know, is the graph a function? That's actually a very easy test. One of these is not the graph of a function. Well, we just said each x should only have one y. So let me pull up my graph paper here real quick. Let's look at that. So if I have a graph, let's just make a kind of a curvy. Okay, is that the graph of a function? Well, it's very easy to test. I'm going to pull out my ruler here. And I'm going to look for an x. Let's say for this x right here. How many y's are there? Well, if we go up, there's only this one. That's the only y that exists for that x. There's one y. How about if I look over here? Yep, that one's only got one y. That's only got one y. If I do x is 0.3 or something, there's still only one y. Every x, when I make a straight up and down line, it only crosses the graph once. There's nowhere that there's two different y's for the same x. So this is a function. If my graph did this, now right here, when the x is 0, look, there are 3 different y's. See, I'm going to mark those in red. For this x, this is a y, this is a y, this is a y. That's not a function. It's not a function because if I say what is the y when x equals 0, well, you have 3 different answers. You should just be able to give me one answer if it's a function. Now, when I look over here, it looks like a function. There's only one y, one y, one y, one y. But if I can find any place that that's not true, it's not a function. So with a graph, all you have to do is a straight up and down line and see, is there any place that I cross a bonus? Well, yeah, over here, there's 3. Over here, there's 3. Right here on the edge, there's 2 because there's one right there at the edge and another one up there. So there's 2. There's 2 that exist right there. 2 that exist over here. Anywhere there's more than one, not a function. So now, looking at this, now it's easy for us to tell which one is not a function. Obviously, it's C, because right here, in between x equals -2 and x equals +2, there are 3 y values for every one of those x's that exist in between there. This one, there's only one y. It goes up and down, but there's only one y. There's only one y here. But this last one, we can see multiple y's for each value of x. It's called the vertical line test. Vertical line. We make a straight up and down vertical line, and it should only touch the graph in one point. There you go. Only if no vertical line intersects the graph in more than one point. Domain and range, we've talked a little bit about that. The domain is all the possible x's. The range is all the possible y's. So when you find the function, you have to make sure all the x's are valid. And then for those valid x's, what can the y's be? So let's see, what else do we have in here? The range is just substituting all the possible x's in. If we look at the graph, it looks like the range would be, it's not going to ever touch this. That's an asymptote at y equals 0, the x-axis. But it'll go all the way up to infinity and all the way down to -infinity. So this is, the range is all y's except for y equals 0. Same thing on the domain. The x's are going to go to infinity and -infinity. But when x equals 0, does not exist. So the domain is all x's except for where x equals 0. Okay. That looks like it for this lesson. Let's go ahead and take a look at the assignment real quick. Determine whether this is a graph of a function. Again, that vertical line test. Determine the domain. What are all the possible x's? All right. What's the domain of this? This is a little more complicated, but still, break it down. You have a square root on top, so the x's cannot be negative. So any x's that would make that negative, and any x's down here that would make this 0. So there's a few different possible answers there. What's the range? So what is the range? Am I limited on the x's? X plus 5 squared plus 8. No, I can put any x from -infinity to infinity. So if I have that, what are the possible y's? You may need to graph that to tell you. You can always put that on Desmos on a graph and check out the range and say, what are the possible y's? And then the fifth one you have to answer. Determine whether the formula describes y as a function of x. Is this a function? Is this a function? Is there only one y for any x you put in there? So you have to explain. It says explain your reasoning. You don't just put yes or no. You have to explain it. Yes or no won't get you all the points. All right, so let me leave that. Let's look at our other lesson that we have this week, graphs of functions. Graphs of function. Graphs tells us a lot about a function. Like we said, this has a link to Desmos right there if you want to use the Desmos, if you don't already have that bookmarked. The graph of a function. Okay, recall the definitions of function and apply it to a graphical representation, right? For any x, there will be exactly one y on the vertical axis. So on the graph, it'll only cross once when you put a vertical line. So let's talk about how we classify function. We classify them as increasing or decreasing functions, right? And that's always going from left to right. As the x gets bigger, 0, 1, 2, 3, 4, 5, 10, a million, 53 jillion, as the x gets bigger, does the graph increase? Does the y increase or does it decrease? That tells whether it's an increase or a decrease. Now this one does both. It is increasing here. See, increasing that when you're starting with the negative x's, but when it gets up here, just past -2, that's a relative maximum, which means it's not the ultimate maximum. Over here, I can find y's that are bigger, but for that area of the graph, that is the largest y. It's a relative, just relative to that area of the max. And then it's decreasing from there until it gets over here close to 2. So this is an increasing function and then a decreasing function, and then it increases again when it gets past that. And there's a relative minimum, not the absolute minimum, because there's a lower values over here when x is at -3 and -4 and -100. So it's not the absolute minimum, but it's a relative minimum. If I'm just looking at that area of the graph, it's a relative minimum. So it says by looking at the graph below, we can see the function is increasing when x is less than 1.5, because that's about 1.5 right there. Anytime it's less than that, it's increasing. And also for x is greater than 1.5, it's increasing. But between -1.5 and +1.5, and between there and there, the y value decreases. So it's called a decreasing function during that interval. All right. Here's more formal definitions. Again, if you want to get into the math part of it. So if we say x1 is less than x, which is less than x2, that says that x1 is less than x2. So if you put values in there, if x1 equals 0 and x2 equals 5. All right, so it's saying that value is less than that because x is less each time. The function f is increasing on an interval if for any x1 and x2, x1 is smaller than x2. So that just means as the x values increase, so do the corresponding y values. That's all that really means. Is if the x is going up and the y is going up, then that's increasing. Just the opposite for decreasing. This means as the x goes up, the y goes down. That's a decreasing function. There's also constant functions. All right. So that means that the y stays the same. It's a horizontal line. Doesn't matter what the x is, the y is a horizontal line. Here we talked a little bit about relative minimum and maximums, right? When it's increasing, decreasing, or constant, the point where the change occurs is either a relative minimum or relative maximum. At that point, right up there on our graph, that point that it changes is the relative maximum and the relative minimum. All right, so a function f of a is called the relative minimum if an interval x1, 2 contains it such that x1 is less than x is less than x2. That means your a is going to be less than the values around it, than the f of x. We'll make it a relative minimum. If you, on either side of a, the y is higher, the y value is larger on either side of a, is a low point, and it is a relative minimum. If on both sides of a, if it's larger, if it's smaller and the a is higher than the points on both sides, that's a relative maximum. That's the high point. So use a graph to find the relative extrema. Again, look at the graph above here. Click on this and we'll look at this. Well, that's not there. I gotta fix that link. There's a relative minimum. That's the graph up here that we looked at. Relative minimum, relative max. That's what that link was going to take you to. And you can use the trace key on your calculator, or you can use Desmos. Let's see if we can make a graph. Oh. Plus x squared. There we go. I just made a graph. And this graph has relative maxima and relative minimum. And we can use Desmos and go along that and find where that point is. See it when x is negative 1.333, the y is 1.185. But if we go on this side, the y is smaller. It's 1.152. If I go on this side, 1.185, 6176. Everywhere I go, I can't find a y that's larger than the 1.185. That is the relative maximum. Same case, I can go to the relative minimum at 0, 0. On either side of it, the y is bigger than 0. Just barely, 0.02, 0.015. But 0, 0 is a relative minimum for this graph. All right, so you can find those using Desmos. You can use, if you're using a calculator, you can use the trace function, the trace key, trace function, and you can find the maximum on there. So, all right, symmetry. Let's talk about symmetry. Symmetry means like a mirror, that if you have symmetry with the y-axis, it means everything on the left is like everything on the right. Let's make this symmetry right here. This is symmetric to the y-axis. If the y-axis, let me make a line for the y-axis. A blue line right there, if that was a mirror, everything on this side is a mirror reflection of everything on this side. That red line on the right is a mirror of the red line on the left because it's symmetric around the y-axis. The y-axis is the blue line. So symmetry is when you have a mirror image. Okay, so a graph has symmetry with respect to the y-axis. If whenever you have an xy, you also have negative xy. So let's look at that. If I have xy, let's see if I can get a nice even x. Sorry, 1, 1. Okay, we have the point 1, 1. That's on our graph. 1, 1, 1. That means we should also have negative 1, 1 on a graph. And we get there, we do. We have negative 1, 1. So if we have xy, we should have negative xy. So since x is 1, if x is negative 1, we also have the same value of y. All right? Negative xy will exist if it's symmetric to the y-axis. The y-axis is like a mirror line. The graph has symmetry with respect to the origin if xy matches the point negative x, negative y. Let's do what is symmetric around the origin. Oh, that's not it. Okay, this is symmetric around the origin. From this point right here, this is a mirror image of everything going the other direction, which means if 1, 1 exists, that means we also have the point negative 1, negative 1, which we do. So negative 1 also exists, just like 1, 1. These points in here, we have negative 0.59205. We have positive 0.59205. All right. Every point that exists as an xy also exists as a negative x, negative y. That's symmetry around the origin. If we spun this around 180 degrees, it would look exactly like the other half of the graph if we rotated it around the origin. So origin symmetry is a rotational symmetry because we can rotate it 180 degrees. A graph has symmetry with respect to the x-axis. Okay, let's look at the x-axis symmetry. Negative x squared. Oh, I'm sorry. X equals y squared. This is symmetric around the x-axis. So since we have 1, 1, we should also have the same value with the negative y. We should have 1, -1. So let's look at 1, -1. Right there. We got 1, 1, and we have 1 negative. The y becomes negative. So every time you find a point on here, the point 4, 2 should also be a 4, -2 if we go down here. Up 4, -2 also exists in the graph. So that is symmetry with respect to the x-axis. So let's look at even or odd. A function whose graph is symmetric to the y-axis is an even function. We call it an even function. So back when we have x equals y squared, I'm sorry, y equals x squared, this red one, that is an even function. And a function whose graph is symmetric to the origin is an odd function. So the odd function would be the red one there. So that is odd. If it was with the y-axis, that's even. So I can change it from an even to an odd. All right. And the graph of a non-zero function cannot be symmetric with respect to the x-axis. Why can this one not be even or odd? It's because it's not a function, right? With that vertical line test, there's 2 y's for this one x. 1, 1. And so when x is 1, there's 2 different y's. This is not a function. That's why it's not an even or odd function, because it's not a function at all. It's got more than 1 y for each x, where these red ones do not. They are functions. So here's an even function, symmetric to the y-axis. It's like a mirror on each side of the y. Here's an odd function, like we had on Desmos there. You could rotate it 180 degrees around the origin, and it's exactly the same thing. Now, here's a test, and I'll show you how to do this on paper here. Here's a test. So let me put this up. If it's even, well, I didn't write that nicely. F of negative x will equal f of x. And if it's odd, then f of negative x will equal negative f of x. All right, I'm going to put this up on the screen here. Okay. So this says if a function's even, f of negative x will equal f of x. And if it's odd. So let's check one. Okay, we said this was one that was symmetric to the y-axis. Symmetric to the y-axis, which means it should be an even function. That means we should be able to substitute negative x into the equation, and it will end up exactly like the original equation. Here's the original equation. So let's substitute negative x in for x. So this will be negative x squared. Okay, so what is negative x times negative x? When you square something, you multiply times itself. Negative times a negative makes it positive, x times x. So that equals x squared. So this equals x squared, which equals the original function. So that means this is even because we substituted negative x in and we got exactly what we started with. And that can be much more complicated equations, but still, if you end up with the exact same thing. For odd, when we did f of x equals x to the third, that was symmetric around the origin. And we said, oh, that's an odd function then. Well, let's prove it algebraically. Let's put negative x in for x. So what's negative x times negative x times negative x? Well, negative x times negative x, we've already calculated. That's up here, x squared times another negative x. So now it's a positive times a negative. So it's going to be a negative. X squared times x is now x to the third. So this equals negative x to the third. It's exactly the opposite sign of what we started with. If we had an equation such as this, this would be an odd function also, we believe. But let's test it. Let's substitute negative x. So it'd be negative x to the third minus x. Oh, I'm sorry. We've got to substitute negative x for that one also. Minus negative x. So we substitute negative x in everywhere we find an x. So we already said negative x to the third equals negative x to the third minus a negative x means positive x. Look at there. That's exactly the opposite. This was a positive, now it's a negative. This was a negative, now it's a positive. Every term should be reversed if it's an odd function. That means it's the opposite on every sign if it's an odd function. For an even function, everything would be the same. If this was plus 4, we'd still have a plus 4 left over here. It'd be exactly the same sign. And you may have some that if this was x to the third minus x plus 1, if that's what our equation was, and we substitute negative x in for that, and we want to know, is this even or odd? So we've got negative x to the third minus negative x plus 1. Well, we know negative x to the third equals negative x to the third. We know subtracting a negative x makes it a plus x. And plus 1 just is plus 1. This is not even or odd because this is exactly the same. That's exactly the same, but the other one's different. Right? These are both different. So since it's a combination, this is neither. This is neither even nor odd. Neither. Let's graph that and see what we see with respect to the symmetry. I'm going to cancel all these here. So if we graphed y equals x to the third minus x plus 1. So that's not symmetric around the origin. If we rotate this around the origin, it's not going to look like the other part. Without the minus 1, we said it was symmetric. Now this, when you rotate this 100 degrees, is exactly on this side. That's perfectly. But when we add that plus 1, it's no longer symmetric to the origin. It's not symmetric to the y-axis. It's neither even nor odd. So that's how you can test it. Substitute negative x in and see, did I get the original equation or did I get the opposite of the original equation, or is it neither? Because it very easily could be neither. So then they give you some examples of that. So, all right, increasing and decreasing. We've talked a little bit about that. Really, since this is a graphs of function lessons, we're looking at graphs. This one on the left, this is increasing the entire time. It's not increasing much, but it's increasing the entire time from left to right. As the x's go from smaller to larger, it's always increasing. The second one's always decreasing, right? It's decreasing a lot and then decreasing a little, but it's always decreasing. Constant. This stays a constant 2 all the time. This one's decreasing, then it's constant, then it's increasing. Sometimes you've got to break that up. So here's tables of the same information. So can you tell which one is increasing, decreasing, constant? Each of them, the x is getting larger from top to bottom. Goes from -2 to 7, -2 to 7, -2 to 7. This one, the y is constant. So this is a constant function. This one is going from 3 to 1 to 0 to -2. The y is going down as the x increases. This is a decreasing. This is b. And this one goes from -5 to -3, -1 to 1 to 4 to 10. This is getting larger as the x's are getting larger. This is an increasing function. So you should be able to look at that and see if the x is increasing, what's the y doing? That shouldn't be too hard to look at. Let's see, this talks about putting things on a calculator with the list. So if you're using a TI-84, there's some instructions over there for you and how to enter that in your calculator. So then this just gives the math definition. A function is increasing on an interval if for any 2 points in the interval, there's a positive x results in a positive f of x or a positive y, right? If it's decreasing, the positive x will go to negative y. If it's constant, positive x, no change in y. Remember, f of x and y are the same thing. Okay, analyzing a function for increasing, decreasing behavior. Solve graphically. Put that on a graph, and you can see where it's increasing, where it's decreasing. Same for that one. There it is in the graph. See, it's decreasing until x equals -2, and then it's increasing after x equals -2. So from a negative infinity to -2, it decreases, and from -2 to infinity, it increases. Okay, here's the other one they had. This one's increasing, and see, it says increase from negative infinity to -1, and again from -1 to 0, but it has these parentheses because it does not include -1. -1 is an asymptote. It never touches -1. Decreases on 0 to 1 and 1 to infinity, but does not include the 1 because it never touches x equals 1. Boundedness. See, the concept of boundedness is understood when you look at it graphically. All right, so is this bounded above or below? No, this will go all the way up to infinity and all the way to negative infinity. There's some values in between it doesn't get, but it's not bounded. This one's not bounded above because it goes to infinity, but it's bounded below. It never gets below that y value right there, that absolute max minimum. This one is bounded above because it never gets above that y value, but below it goes forever. And this one's bounded top and bottom because that's not even arrows, so they don't continue. This graph never gets higher than that y or never lower than that y. It is a bounded graph. So there you go. A function is bounded below if there's some number of b that's less than or equal to every number in the range. Lower bound, upper bound, bounded. Okay. Local and absolute extrema. That's what we're talking about, maximums and minimums. This has a absolute minimum right here on this graph, and you see on the left, that little blue dot that's an absolute minimum. This is a relative minimum. For the area right around it, this is the smallest y. So this has a relative minimum and an absolute minimum. Absolute means there's no other minimum smaller than this. It has a relative maximum between 0 and 1, when x is between 0 and 1, but it does not have an absolute maximum because it goes to infinity. So you need to be able to identify the local extrema, the local maximums, the local minimums, the absolute maximums, the absolute minimums. And that's generally done by graphing is the easiest way to do that. Symmetry, you can do that graphing. You can see it on a table sometimes. It goes 9, 4, 1, 1, 4, 9. You see symmetry there. And with the algebraically, remember, we can substitute that negative x in and see if there's symmetry. All right, and then there is with the x-axis, symmetry, x equals to y squared. You see that there, the x is 9, 4, 1, 1, 4, 9. And algebraically, they're not functions, but we can say if there's x negative y, there's also xy. And the origin. So negative x would be negative f of x. And we see numerically on the table or graphically. So you can check functions for symmetry, and that is the last of that page. So, all right, let's look at the assignment that goes with 2.02, and then we'll let you guys out of here. Determine the intervals when it's increasing, decreasing, or constant. Look at that graph. Is it ever decreasing? Is it ever constant? Or is it always increasing? And these gives you choices. Use the graph of f, this is the graph, to estimate the local maximum, local minimum. You got to estimate when are the local maximum, local minimums. Okay. Determine algebraically whether this is odd, even, or neither one. That's where you substitute negative x and simplify it. And do you get the exact same equation? Do you just get the negative of the same equation or neither one? And then here you have to give an example of an even function. If an even function, and explain algebraically why it's even, which means you have to substitute negative x. If you're explaining algebraically, then you're substituting negative x into it. So you get to write an even function and substitute negative x to prove that it's even. All right. So this only has 4 questions, but one of them is that you've got to write it all. So that's what our lesson is for this week. That's where you stand. So if you have any questions, hang around. make sure you're done with module 1. If you're not done with that, you don't need to start a module 2. You need to finish module 1 first. But get that done, and we'll see you Wednesday if you need to be here. If you didn't turn in the test, you need to be here because your grade's going to be below 70 by Wednesday. So see you then.